Okay, today we're going to finish up chapter 1 by covering section 1.5. Now this one I do have a PowerPoint for, but while you're watching the video, what I would do is just have those guided notes printed out. You will not need the PowerPoint pulled up. I'm going to just use that to go through the guided notes with you, so you can fill those in as you go. What we're going to cover in section 1.5 is visualizing functions. So we just talked about last time functions and what they are, how to use that function notation. And this time we want to talk about kind of a bunch of different elements that we like to look at in functions, especially when we're looking at their graphs. That first element we want to talk about is finding the maximum and minimum values of a function. When we find that maximum and minimum value of a function, the words are kind of good for this, right? It is what you think it is. It's the highest value and the lowest value that this graph can reach. So as you're looking at this graph, can you guess what that maximum value would be? Now the key here, the important part, is to make sure, is to make sure that you're always thinking about the y value here. So our max value is as high as the graph will go, because y values go up and down. It's as high as the graph can get and as low as the graph can get. We're not talking about maximum and minimum as far as the x values go. Because when we talk about the maximum and minimum a function can hit, we're talking about those output values. So how high does this graph go? And if you were to give that maximum, we would be looking at that very top point up there, and you would give the y value. So the maximum is 15, that would be your answer. And it occurs when x is 13, but we wouldn't need that part. I'm just putting that part in there so you are clearly identifying the difference between those two values. The maximum here is 15. Can you then find the minimum? And on this one, it gets maybe a little bit tricky just because it's not where the graph starts. Minimum and maximum values do not have to be where the graph starts and ends. The maximum here happened to be when the graph ended, as we're looking at it from left to right, but the minimum will actually occur where it hits its lowest point, which is here, somewhere in the middle, right? We're looking at this point down here. So when we're looking at that point, again, we want to report the minimum as the lowest the graph goes, which is a y value. So there you would report a minimum value of -5. That occurs when x is 5, but the value we want to report as the minimum is -5. Okay, now I do want to talk about what happens when a graph goes on forever. So this particular graph had very clear endpoints. This next one we're going to look at is one of those that does not have the clear endpoints. So this is one that we assume goes on forever, which is going to be important when we're thinking about that maximum value. So because the graph goes on forever, we assume that there are those arrows there that make it go up forever. As we think about what's the highest value this graph can reach, there isn't a highest value. It goes on forever. Now, when we were talking about like domain and range of graphs before, we used infinity for that. But here, that maximum infinity is not a number. So what we're going to say is that the maximum doesn't exist to represent that it goes up forever. Here, though, we do have a minimum. This graph has a lowest point that it will hit. And that lowest point occurs there at the bottom, right? At the bottom of that curve. The lowest point that graph hits then, what's the y value? And be careful of your scale here. So notice 4 steps gets us to -2. So that minimum value with the scaling of the graph the way it is, always pay attention to that, is -1. And it occurs when x is 0, but again, we report that y value for the minimum. So hopefully that's starting to make sense, and I want to just make sure it makes sense. So as you see in your guided notes there, can you now draw a graph that has no maximum or minimum value? What do you think that would look like? So your maximum doesn't exist and your minimum doesn't exist. There are several different ways this graph could look. I'm going to give you just a few examples here. A line would be an example of a graph that has no maximum or minimum. Okay, this goes up and down forever. Another example could be something that kind of curves in the middle, and that's okay. It could curve even more in the middle, and it would still go up and down forever, right? So we can have even more variation there in the middle, and as long as the graph goes up and down forever, it has no maximum or minimum value. All right, so those are just a bunch of different examples. They can have these, kind of what are actually called local maxes and mins when we have those little curves in between. But what we're looking for is the overall what happens to the graph. All of these graphs would have a maximum that didn't exist and a minimum that didn't exist. Okay, so that's all about maxes and mins. The next thing we want to visualize about functions are where our outputs are positive, negative, or 0, and where those changes occur. Okay, so again, we're going to be working with interval notation here to report, because there's going to be intervals where these things are true, to report where the graph is positive, negative, or 0. Now, we're looking then again for where the output is positive, negative, or 0. Okay, so you're looking for where the output is positive, negative, or 0. Now, when you change from positive to negative, you hit 0. So we're actually going to find those zeros first. Those aren't going to be intervals. Those are going to be very specific points where our function is 0. And then those points will help us find the endpoints of the intervals where we're going to end up being positive and negative. So where is your graph? Where do you have an output of 0 on your graph? Can you list those x values? In this case, there's going to be more than one 0. This is kind of what we did back in the last section, right? We're asking for an input given an output. So those inputs where our function is 0 are given by those points that I've starred there. Be careful of the scale here. Those x values should be -8, 4, and 12 as you move across those points from left to right. Okay, so the graph hits 0 at those points. And now what those points are doing are breaking up our graph into its intervals of positive and negative outputs. So as you look at the graph from left to right there, your first interval there is going to be a positive interval because that entire part of the graph is up where we have positive y values. It's above the x-axis. So can you find the intervals? And there, I just clicked it through, but those are the intervals then. Any interval above the x-axis is going to be where you have positive outputs. Can you then give the interval notation for those answers? What is the interval notation showing those two intervals where our graph is positive? And again, be careful of the scaling here. Each step here is worth 2. So for that, you should have gotten forever to the left, our graph is positive up until the x value of -8. And then it's positive from the x value of 4 to 12. Notice here that all of those numbers have parentheses and no brackets, because to be positive, we are greater than 0. And the -8, 4, and 12 were all where we were 0. So we will not include those points because those points are at 0. So if you're not actually above the x-axis, we're just getting really close to those points, but we can't actually be those points because then we will be 0. Okay, what about where our graph is negative? That would be the remaining portions of the graph or the portions below the x-axis. So those two portions there. Can you report the correct intervals for that? And the two correct intervals there are going to be from -8 to 4, and then from an x value of 12 all the way to an x value forever positive. Forever to the right, that graph is going to stay below the x-axis and have a negative output. Now, one thing I do want to point out is this new symbol that we probably haven't seen before, right? Which is this U you're seeing here. Basically, it looks like a U. It's how you join two intervals. So since there was 2 intervals that were positive and 2 intervals that were negative, you use this union symbol between intervals to show that both of those intervals are included. And you'll still want to make sure it's always your lowest interval, then your highest. Make sure these intervals go from left to right on a number line. Okay, so that's how you'll do more than one interval, is by just joining multiple intervals with what's called that union symbol. All right, increasing or decreasing is our next topic. So we've done max and min, we've done positive, negative, or zero on our graphs, and now we want to look at the graph and identify, okay, where would the graph be increasing and where would the graph be decreasing, and what does that look like? Now again, it's very important here that you realize we want our output to be increasing, our output to be decreasing. We're never talking about the input changing here. We're talking about how the function is changing, so we're talking about how the output is changing. As you think about the visualization there about what does decreasing look like, decreasing can look like a decreasing line, or you can kind of be changing the rate at which you're decreasing. But for instance, that line the entire time is decreasing. Okay, so anything that looks like that, anything that's going down from left to right. Anything that's increasing could be a steady increase of a line, or again, it could be changing how fast it's increasing. That line is increasing the whole time. Okay, anything that is perfectly flat, which I don't think I can even get that perfectly flat, but imagine that, a perfectly flat line, that would be something that's constant. So it would go in neither the decreasing or increasing interval. You have to be continually going up from left to right. Okay, a perfectly flat line is constant. So let's see if we can look at a graph and give the intervals where it's increasing versus decreasing. Here's the graph we're going to look at first, the same one in your notes. Okay, so as you look at that graph, can you figure out where it's increasing? Let's do increasing first. And again, make sure here that your y is increasing, so it's looking like the examples I just gave you. And make sure that when you give those intervals, you don't include those points that are the endpoints of where it changes from increasing to decreasing. Because if you think about being at any one point you're constant. So these increasing or decreasing intervals will always have parentheses every single time. All right, so did you get that increasing interval correct? Hopefully you were looking at that interval and the next interval there that's highlighted. So we're increasing in the intervals negative infinity up to -8, and then again from -2 to 5. But again, I will not include those endpoints by putting brackets. I will only have those two intervals, and then I can join them with a union sign for my final answer. My decreasing intervals are what's left over, right? The red parts that are left over are where my graph is decreasing. That means it's decreasing from -8 to 2, and it's decreasing from 5 to infinity. And both of those intervals were decreasing the entire time. So this particular graph was never constant because there was never a flat line that was part of this graph. Okay, and again, you would report that final interval with a union sign to join those two intervals and show that in both of those intervals, we were decreasing. All right, so hopefully that made sense. That's increasing versus decreasing. You're going to get a lot of good practice with all these different things in the homework as well. Our very last topic that we want to be able to identify when looking at a function that is graphed is what's called concavity. So when I'm talking about concavity, there's two types of concavity. There's concave up or there's concave down. And what that looks like is whether or not basically you have an upside down bowl or a bowl like you would normally see, okay? A typical bowl is where you're concave up. So this would be a graph that is concave up. Now you do not have to have both sides of that bowl to be concave up though. This graph is concave up and this graph is concave up. It just has to have the right curvature. So if we're concave down, that means I have an upside down bowl type of curvature. And that means I can either have this side of the bowl or I can have this side of the bowl and still be concave down. I just need that curvature to have that type of concavity. Okay? Now, just like it was important to find the zeros to identify the difference between a positive and negative interval, and to find those differences between those endpoints between a increasing and decreasing interval, it's going to be easiest to identify this concavity if you first identify what's called the inflection point. Okay, the inflection point is where you change from a concave up graph to a concave down graph. So I'm going to try and draw that here for you so you can kind of see what I mean. So as I draw a concave up graph, if you draw that and then switch it to concave down, you'll notice your pen direction changes, right? You have a point as you're drawing this where you kind of have to flip directions to draw the concave down. So somewhere around right here, you're switching from concave up to concave down, and that is what your inflection point is. Now, this is not going to be as easy of a point to identify as it is to identify where a graph changes from positive to negative or increasing to decreasing. So always identify, estimate. This is going to be an estimation. You might see it at a slightly different place than I see it, but it's all going to be in about the same place. So identify this point first, and then that will help you now give the interval for where you're concave up versus where you're concave down. Okay, so always identify that inflection point first. That's going to make your life a lot easier when you're coming up with these intervals. Sorry, I didn't mean to get that line there. Let me see if I can get rid of that. There we go. Okay, so identify inflection points before you start to identify those intervals where you're concave up or concave down. We're going to do an example of this. Okay, so as you flip the page in your notes, you'll see a graph come up, and we're going to identify those points of inflection and then where this graph is concave up versus concave down. So you might be jumping into saying, okay, where is this concave up? But stop yourself and find those inflection points first. So where are we changing from concave up to concave down? Where are we changing from concave down to concave up? So those points of inflection should be somewhere in the middle between those bowls, right? So you actually have 2 points of inflection here. I'm estimating them to be around an x value of -5 and an x value of 1. You might have been slightly different, but make it easier on yourself at least and pick an x value that's pretty easy to read here. Okay, so that's where I've estimated my points of inflection. So now I'm able to clearly identify where I'm concave up versus concave down. So I'm going to start with identifying my concave up intervals. So which parts of these graph, which part or which parts of this graph are concave up? So hopefully you identified that middle portion there as being concave up. That's the part that's going to hold water. It has the curvature of a bowl that would hold water. So how do you report that interval? Make sure you're reporting the input variable, the x variable in this interval, okay? So it goes from an x value of -5 to an x value of 1. Now, if you think about being at -5 or at 1, at any one point, do we have any curvature at all? And the answer is no. So again, with concavity, you will not include any endpoints. So with all of your concave up and concave down intervals, just like with your increasing versus decreasing, you will always have parentheses. And that's our only concave up interval. So we don't need any union symbol here. The rest of the graph is concave down. So when we report that concave down interval, can you get those two intervals correct? Did you get that it was concave down from -infinity to -5, and then again from 1 to infinity? So basically the remaining portions of that graph. Again, you would only not have a concave up or concave down graph if you had a perfectly straight line, either vertical or horizontal, or just a perfect line in general that wouldn't have any concavity. But this entire graph has curvature, so the entire graph has concavity. And then we would just put a union symbol between those two intervals as our final answer. So I feel like in general, this kind of seems like, okay, I get maybe what each one of these things are, but why is it important to identify all of these things? So we want to look at the big idea here, understand why all these different things are important elements of a graph. And we're going to do that by looking at this next example here. We're going to try and get the big idea by looking at this real life scenario. This particular graph shows the height of a roller coaster track over the time of the ride. Okay, so over time, how is the height of the roller coaster track changing? And we're just looking at some arbitrary times. So from time 0 to time 8, we don't exactly know what that means. Okay, and it goes from height 0 to height 4. We don't have units there or anything, but that's okay. We're just getting a general idea of what is happening over time to the height of this roller coaster track. So things like where the graph hits a maximum, that would be the maximum height of the roller coaster. That's an important point in the roller coaster ride, right? Something different happens at the maximum point of the roller coaster ride versus the minimum. A roller coaster certainly acts different as the height decreases versus when the height increases. Those have different meanings when we look at this in terms of an application. Whether or not this roller coaster is concave down or concave up tells us what type of ride we're going on, right? So this graph is mostly, we're seeing both concavities here. At first it's concave down and then it switches around 2 to be concave up till about 6 where it switches to be concave down. And that's telling you something about how the ride is going, right? We want that curvature. That's what makes the transition smooth in a roller coaster ride. All of those things are very important. Now, all of these things are also very important as we start to analyze this graph and think about, okay, if we know the height over time, can we use that to generate an entirely new graph that for this same roller coaster looks at the speed of the roller coaster over time? How should that speed graph look? Again, you're not worried about the numbers here. Your time should still go from 0 to 8, but you don't know exactly how your speed should change as far as from what number to what number. But you know that if your roller coaster is going down in height, what should happen to your speed? If your roller coaster is going up in height, what should happen to your speed during that same time interval? Things are going to change based on that height. So see if you can generate a general. Now all of our graphs will be a little bit different, but certain things should be happening around the same times. Our speed should be increasing around the same times, decreasing around the same times, okay? Based on this height graph of our roller coaster. So can you generate that speed graph? Pause the video, try and generate it, and then see if you get close to what I generate. Okay, so this is the graph I generated for the speed. Mine also went from time 0 to time 8. Now notice a few things here. The first part of my graph decreases in height here, and as I go down a roller coaster, what happens to my speed? My speed will increase as my roller coaster is going down. Then as my roller coaster starts to go up, what happens to my speed? My speed will decrease. Couple very important things here, right? It'll increase and decrease pretty fast, right? It'll get faster and faster as I go down the graph. And as soon as I hit that bottom of the roller coaster, I'll start to slow down. So I had those things occur around the same time, okay? Also, this graph won't necessarily stop at the end, right? It'll just go back up to a peak. I might still be going after this. It might be the end of the ride and you had it stop, but I decided it wasn't quite the end of the ride yet, and my speed was still at just a low speed comparatively, but still going, okay? All of these things were important. I knew that if my height was decreasing, my speed needed to increase. My concavity basically flipped here for my speed graph. okay? Where I hit maximum heights, I should hit some minimum speeds. Where I hit minimum heights, I should hit some maximum speeds. Things like that go hand in hand. All of those elements come into play in this graph. Things like both height and speed should be entirely positive graphs, right? You can have some zeros, but we shouldn't have any of this below zero. We should have no negative outputs here because speed and height are all positive values. Now you could argue that with height, maybe if you're talking about like above sea level versus below sea level or things like that, you could argue some negative heights, but we're going to keep it fairly simple for this and keep it all above sea level or above ground or whatever you want to think, okay? But all of those things come into play. These are all the types of things you're thinking through, even if you don't realize it, when you go to generate and analyze a graph. Okay, so I want to do one more of these. And again, make sure you're thinking through all of these different elements as you come up with a graph that will represent this next scenario. So your scenario is given, and you're going to create a speed versus time graph again. This is talking about a child in a playground climbing the steps to a large slide, first at a steady pace, then gradually slowing down until she reaches the top before she stops to rest, where she stops to rest before sliding down. So you're only picking out the parts here that are talking about the speed of the child. So at the beginning, what's her speed? At the end, what's her speed? What's happening to her speed in the middle? Should it be increasing or decreasing? How fast should it be increasing or decreasing compared to what she was doing before? Okay, so all of those things need to come into play. So again, pause the video and see what you get. Again, yours can be slightly different than mine, but key elements should be the same. Okay, so this is my graph of her speed versus time. So we started off at a steady pace. So it was very important here that wherever your speed is at, it's above zero and it's steady for a certain amount of time, meaning that your speed stays constant for a certain amount of time. Then she slowed down. So it's very important that at some rate, you're slowing down for a period of time. And it also says until she reaches the top where she stops. So it's very important that you have a speed of zero for a certain amount of time where the child stops at the top of the slide. Then she slides down. So what's happening here? Her speed is going to increase, and it should be increasing fairly rapidly, right? Because she's going down a slide. And it should also then decrease very rapidly because when you come to the end of a slide, you very quickly come to a rest, right? Your speed goes up as you go down the slide and very quickly comes all the way back down to zero where you stop at the bottom of the slide. Okay? Also, comparisons here are very important. So let me get rid of all of these things real quick. The comparison between these steepnesses here. I don't know if steepnesses is a word, but we'll go with it, okay? So thinking about the difference between how steep my first decrease was versus how steep my decrease was at the end of the slide. Certainly this first decrease as I'm just slowing down as I'm walking up the stairs should be slower than when I come to a stop at the end of the slide. And my steepness going down the slide, I'm probably going to go faster than when I was walking, right? As I go down the slide, I go pretty fast. We always get a rush from going down the slide typically, right? So that was a much steeper line than my decrease over here, okay? So all of those things come into account, not just if we're increasing or decreasing or constant, but also how fast we're doing those things, okay? I also did things like decided not to have some curvature, whereas you maybe did, okay? But I especially thought like on the slide, when I come to that direct stop, that's not maybe happening at a gradual pace, but very quickly turning downward in my speed. So you could have had more curvature in your graph. That would have probably been just fine. Again, we're all going to justify these things a little bit differently and as to how there's a lot to interpret here, but there are some things that, like I was going through the graph, that are not interpretable. You have to be constant, and you have to be going down to zero. You have to be constant at 0, and then you have to be increasing and decreasing to go down the slide for your speed. Okay, so some of those things cannot be changed. All right, so hopefully you found that interesting. I always really like this section and how it all comes together at the end. Give that homework a try and let me know if you have questions. We're done with chapter 1, so that's awesome. We're ready for chapter 2 here coming up.